Okay, this is complex numbers in polar form part 2. Fasten your seatbelts, ladies and gentlemen, because we're going to go very quickly through this material. You may need to pause if you need to catch up and write some things down or listen a little more carefully because I'm going to go fast. In part 1, we learned rules for computing z1 times z2, z1 divided by z2, or raising a complex number z to a power. We're going to put those rules into a place. We also need to remember that the final answer has to be in the form where theta is between 0 and 2 pi. So sometimes I'm going to have to add 2 pi or subtract 2 pi to get an equivalent angle that is in this domain. So starting out with example 1, I would suggest that you draw a line down the middle of your paper. Somehow I didn't have my line going here to separate the two sides because you're going to need to have all your work, for example 1 on the left hand side so that you have room for your work, for example 2 on the right hand side. Okay, example 1, part A, we're going to do z1 times z2. Recall that to do z1 times z2 we multiply the r's and add the angles. So this is going to equal, I think I'm going to have to put this on a separate line, the square root of 2 times 2 the square root of 2 times cosine of pi over 4 plus 5 pi over 4 plus I sine of pi over 4 plus 5 pi over 4. Simplifying, that gives us square root of 2 times square root of 2 is 2, so 2 times 2 is 4. Then this is cosine of 6 pi over 4 plus I sine of 6 pi over 4, and reduce the fraction, and we get 4 cosine 3 pi over 2. That's supposed to be a pi. Let's do that again. Equals 4 times the quantity cosine 3 pi over 2 plus I sine of 3 pi over 2. So that is our final answer for the multiplication. For part B, now we are dividing. So we're going to do r divided by r. So z1 over z2 is r1 divided by r2, square root of 2 divided by 2 square root of 2. And then we subtract the angle. So remember, multiply, multiply and add. Divide, divide and subtract. So 3 pi over 2, undo, pi over 4 minus 5 pi over 4 plus I sine of pi over 4 minus 5 pi over 4. Notice that you have to write small in here. To simplify that, then that's just going to be 1/2 cosine, well, 5 pi over 4 minus, or pi over 4 minus 5 pi over 4 is negative 4 pi over 4. I'm going to go ahead and write this line, but some of you are realizing that's just negative pi, and that's fine if you just go ahead and write that down. Negative 4 pi over 4. So this is 1/2 times cosine of negative pi plus I sine of negative pi. But we have a problem here. Negative pi is not in our domain from 0 to 2 pi. I need to find an equivalent angle that is, in other words, an angle in the same position on the polar grid that has an angle that's between 0 and 2 pi. So if we think about that, the angle negative pi is going this direction, and it ends up over here on this axis. If I were to add plus 2 pi to both of these, add plus 2 pi to the angle, I would get the angle pi, and the angle pi is just in the same place. So the equivalent form when I add 2 pi to both of these is just cosine of pi plus I sine of pi. So there's the answer to part B. Bring down my line here. Part C. Thankfully, part C doesn't quite take as much room. Part C is z1 squared, which means I square my r and I multiply my theta by 2. So r squared would be square root of 2 squared times cosine of 2 times pi over 4 plus I sine of 2 times pi over 4. So that ends up being 2 cosine. 2 times pi over 4 is 2 pi over 4, which is the same as pi over 2. So this is just 2 times cosine of pi over 2 plus I sine of pi over 2. Pi over 2 is between 0 and 2 pi, so I'm done. And the last one, sloppy drawing there. The last one is z2, back up on that, z sub 2 cubed. So I start out with 2 the square root of 2 cubed times cosine of 3 times 5 pi over 4 plus I sine of 3 times 5 pi over 4. Well, 2 square root of 2 cubed is 2 times 2 times 2, which is 8. Square root of 2 times square root of 2 times square root of 2. Well, square root of 2 times itself is 2, and then you have another square root of 2 left over. So basically it's 8 times 2 square root of 2, which is 16 square root of 2. Write it out if you need to convince yourself. Then this is cosine of 15 pi over 4 plus I sine of 15 pi over 4. Now 15 pi over 4 is bigger than 2 pi because 2 pi is 8 pi over 4. So basically I need to subtract 2 pi from both of these. So I'm subtracting 2 pi or minus 8 pi over 4 from both of these. So my final answer is going to end up being, back to my skinny one, 16 pi over 2. Let me extend the page a little bit here. 16 pi over 2 times cosine of 15 pi over 4 minus 8 pi over 4, which gives me 7 pi over 4. And that is between 0 and 2 pi, so then I'm good. I sine of 7 pi over 4. So that's my final answer. Okay, now we're going to do it. These were all ones that had special angles in them in terms of pi. Now we're just going to look at angles that are just radian angles that are not in terms of pi. I will end up scrolling back down, so if you missed that, or you can always pause the video, remember, and go back and write something down if you didn't see what I wrote at the end there. So part A, z1 times z2. So think about this. Multiply the angles, 2 times 5. Multiply r, add the angles. Cosine 2 plus 4 plus I sine of 2 plus 4. So this is just 10 cosine 6 plus I sine of 6. Pretty easy. That, and we're done. That's all. 6 is in between 0 and 2 pi because 2 pi is 6.28, so I'm good. B, divide. z1 divided by z2. 2 divided by 5. Cosine of 2 minus 4 plus I sine of 2 minus 4, which is 2/5 cosine negative 2 plus I sine of negative 2. But wait, negative 2 is not between 0 and 2 pi, so I have to add 2 pi plus 2 pi. And I could get out my calculator and do this, or I could think, 2 pi is approximately 6.28. So if I add 6.28 to negative 2, I get 4.28. So rather than pulling out the calculator, I'm just going to use my knowledge of 2 pi to do this a little faster. Cosine of 4.28 plus I sine of 4.28. And I'm done. See, this isn't really so bad. You just have to remember the rules. And that's, of course, the part that you don't know as well as I do. But once you remember the rules, it's pretty simple to do these. Okay, next one is z1 squared. So I'm going to have to go back and look at what z1 says. That would be 2 squared. So remember, raising the power, you square r, and you multiply the theta by that power. So cosine of 2 times 2 plus I sine of 2 times 2, which is 4 times cosine 4 plus I sine of 4. 4 is between 0 and 2 pi, so I am done. And part D, last one, z2 cubed is 5 cubed times cosine, I gotta see what the angle is, the cosine of 4, cosine of 3 times 4 plus I sine of 3 times 4, which is 125 times the quantity cosine 12 plus I sine of 12. 12 is bigger than 2 pi because 2 pi is 6.28, so I have to subtract 2 pi, which is approximately or minus 6.28 from both of these from 12. So that turns out to be about, when I subtract 6.28, I end up with 5.72. So this is cosine of 5.72 plus I sine of 5.72. So those are the polar form. Now you might wonder why we're doing this, but it is leading up to something kind of useful on Monday that has to do with this. So this is just kind of practice using the operations right now. The last question is asking you now to confirm that the answer in polar form and the answer in rectangular form actually are the same by plotting it on the graph and looking at it, putting it in both forms and then graphing. So part A, I'm going to have to go back and look at see what part A was. It was 4 cosine 3 pi over 2 plus I sine of 3 pi over 2. So 4 cosine of 3 pi over 2 plus I sine of 3 pi over 2. So I'm going to put this in A plus BI form. To do that, I just have to remember that A is r cosine theta and B is r sine theta. So I'm going to write this as 4 cosine 3 pi over 2 plus 4 sine 3 pi over 2 times I. So if I find 4 cosine 3 pi over 2, that's my A. 4 sine 3 pi over 2 is B. 3 pi over 2 is a special angle. So if I recall that my little cosine graph looks like this, and my little sine graph looks like this, and figure out where's 3 pi over 2. Remember, if we divide this into fourths, we go all the way from 0 to 2 pi. So where's cosine of 3 pi over 2? Right here. So it's 0. Sine of 3 pi over 2 is down here at negative 1. So this could be replaced as 4 times 0 plus 4 times negative 1 times I. So in A plus BI form, it's just 0 minus 4i or negative 4i. Now, if I draw a picture of this negative 4i, it should also be a picture of 4 cosine 3 pi over 2 plus I sine of 3 pi over 2. So I'm going to draw a little graph. Negative 4i is just negative 4 in the direction of the imaginary axis, which is the y-axis. So here's negative 4i. Now let's see how that matches up with what I did before. So here's my r is 4. That makes sense. And here's my theta. That is the angle 3 pi over 2. So yes, everything matches up just like I thought it should. So this is always a way you can check to make sure polar form and rectangular form match up to what they're supposed to be. 2C says that I got, for my polar form of my imaginary number, I got 4 times cosine 4 plus I sine of 4. Putting it in A plus BI form would be 4 cosine 4 plus 4 sine 4 times I. So I have to figure out what those two numbers are. Those are not special angles, so I have to do that on my calculator. When I do that on my calculator, I get negative 2.614 minus 3.027i. So the question is, if I graph that, does that look the same in rectangular form and polar form? So this is a quadrant 3. Complex numbers located in quadrant 3. So 1, 2, 3, 4, 1, 2, 3, 4. If I plot that, negative 2.6, negative 3.027 is about right here. So that's what it would look like in rectangular form. In polar form, my radius would, so let me actually kind of draw a little triangle here. So this is negative 2.6. This is negative 3.0, you know, if we round it a little bit. And this is 4. Well, that makes sense. That would be a reasonable right triangle. And then what's the angle? The angle is 4 radians. Well, does 4 radians end up in quadrant 3? Yes, it does. So that makes perfect sense. All of those match up nicely. If you had trouble understanding this, if I went really fast, remember you can go back and check the video out over again and have fun. Glad you enjoyed. Bye, as Dixie would say.